Today we are going to do chapter 5 and chapter 6. Questions 1. A current of 3.2 ampere flows in a solenoid which is 15 cm long and has 500 turns, each of diameter 2.4 cm. A such coil which has a 20 turns is wound over the solenoid as shown in figure 1. Calculate the magnetic flux linkage within the such coil. To calculate the magnetic flux linkage within the such coil, let's apply the equation. Flux linkage is equals to N phi. N phi is equals to BA cos theta. Now, since you are given the such coil is wound over the solenoid, as shown in the diagrams right here. So as you can see in the diagram, the magnetic field at the center of the solenoid would be equals to the magnetic field passes through the such coil. So we have B solenoid, which refers to the center of the solenoid, is equals to B coil. And since both of them, they have the same cross-sectional area, therefore we can say phi solenoid is also equals to the phi coil. So let us calculate the magnetic flux passes through the such coil first. So phi coil is equals to mu naught N solenoid I over L A cos theta, where this part is the equations to calculate the magnetic fields of the solenoid at the center of the solenoid. So substitute the values into the equations and you will get magnetic flux equals to 6 times 10 to the power of negative 6 Weber. However, even though we say phi coil is equals to the phi solenoid, but it doesn't mean that the flux linkage should be the same. Flux linkage for coil is not the same as the flux linkage for solenoid because the numbers of turns across the solenoid is not equals to the numbers of turns in the coil. So magnetic flux linkage for coil is equals to N coil phi coil. Substitute the values into the equations and you will get 1.2 times 10 to the power of negative 4 Weber. Questions 2a. The current in a circuit changed from 22 ampere to 0 in 5 milliseconds. If the average induced EMF is 220 volts, how much energy was initially stored in the magnetic field of the inductor? B. A coil with diameter 5 cm and resistance 25 ohm placed in uniform magnetic field, B equals to 0.8 Tesla. The coil is placed perpendicularly with magnetic field. Then the coil is moved out from the field within 50 milliseconds. Calculate the energy formed in this process. To find the energy stored in the inductor, let's apply the equations for energy stored in the inductor. U equals to 1 over 2 Li squared. Now we have I already, but we don't have L. However, we do have the EMF. So let us calculate the self-inductance by using the EMF given. So EMF equals to negative L di over dt. Substitute the values into the equations. Self-inductance is equals to 0.05 Henry. Now that we have self-inductance, let us calculate the energy stored in the inductor. So U equals to half Li squared. Substitute the values in the equations and you will get energy equals to 12.1 joule. Now, since question is asking for the energy initially stored in the inductor, therefore we use the initial current in our calculations. Questions B is also asking for the energy, but now it is asking for the energy formed in the coil. It is not asking for the energy stored in the coil. And some more, you cannot apply the equations for energy stored in the inductor because there's no change in the current, no induction process in this case. And this question, it involves motion. It is caused by motion. Thus, we can use the equation from SEM1, which is E equals to V squared T over R, equals to EMF squared T over R to calculate the energy formed in the coil. Let's determine the EMF in the coil by using EMF equals to NA dB over dt. Now, the reasons why we use equations with dB over dt, because we move the coil from inside a magnetic field to somewhere without magnetic field. There's a change in magnetic field in this case. So substitute the values into the equations and you will obtain EMF equals to 0.031 volt. So energy caused by the motion is equals to 1.92 times 10 to the power of negative 6 joule. Question 3 is a long question. Let us focus on question 3a first. A 1 volt AC supply is connected to a 500 ohm resistor, a 100 picofarad capacitor, and a 0.4 millihenry inductor as shown in figure 2. If the circuit operates at a frequency of 500 kHz, determine 1. the RMS current in the circuit, 2. the average power dissipated in the circuit, 3. the power factor of the circuit. To determine the RMS current, first you need to know what type of circuit you are looking at. So given RCL circuit, therefore IRMS is equal to VRMS over Z because it is a combination circuit. So now let us calculate the impedance first. To calculate impedance, let us start from the reactance. So XL equals to 2 pi FL. Substitute the values into the equations and you will get 1.26 times 10 to the power of 3 ohm. Next, let us calculate XC. XC is equals to 1 over 2 pi FC. Substitute the values into the equations and XC is equals to 3.18 times 10 to the power of 3 ohm. So now that we have everything we need, let us calculate the impedance by using Z equals to square root R squared plus XL minus XC squared. Substitute the values into the equations and Z is equals to 1.98 times 10 to the power of 3. Now that we have Z, let's calculate the RMS current. So IRMS equals to VRMS over Z. Substitute the values into the equations and IRMS is equals to 5.05 times 10 to the power of negative 4 ampere. Question 2. Determines the average power dissipated in the circuit. So to calculate the power dissipated, let's apply the equations. P average equals to I squared R. Substitute the values into the equations and we have 1.28 times 10 to the power of negative 4 watt. Now, why we just use R in our equations but not Z? Because there's no dissipation power in capacitor and inductor. Both capacitor and inductor, they just store energy. Question 3 determines the power factor. First of all, we need to know what is power factor. Power factor is cos theta. So to determine cos theta, it is always a good idea to have the phasor diagram first. So if you look at the phasor diagram, now since my XC is larger than XL, therefore Z is located in the fourth quadrant. So the angle is located between Z and R. So in this case, cos theta is equals to R over Z. Substitute the values into the equation. Cos theta is then equals to 0.25 without unit. So we are done with questions 3a. Now let's look at questions 3b. The frequency of the source is then adjusted so that the power factor of circuit is equals to 1. Determine 1. the frequency of the source, 2. the RMS current in the circuit, 3. the readings of V1, 4. the readings of V2, 5. the readings of V3, 6. the readings of V4, and the last questions, the readings of V5. To determine the frequency of the source, first you need to know what happens in the circuit right now. So if the power factor of the circuit is equals to 1, it means the circuit is now operating at resonance frequency. So for resonant frequency, Fr is equals to 1 over 2 pi square root Lc. Substitute the values into the equations. Resonant frequency is equals to 7.958 times 10 to the power of 5 Hertz. Here determines the RMS current. Since it is operating at a resonant frequency, so now Z is just equals to R. Therefore, IRMS is equals to VRMS over Z. But now in this case, you substitute Z as R, which is 500. Therefore, IRMS is equals to 2 times 10 to the power of negative 3 ampere. Question 3 determines the readings of V1. So let's look at the diagram. So according to the diagram, V1 is the potential across the resistor. Therefore, V1 is equals to VR and it is equals to IRMS R. So substitute the values into the equations. VR is equals to 1 volt. So the readings of V1 in this case is equals to 1 volt. Determines the readings of V2. So V2 is the potential difference across the inductor. Therefore, V2 is actually equals to VL, which is equals to IRMS XL. So to determine the values of V2, let us determine the values of XL first. XL is equals to 2 pi FL. Substitute the values into the equations. XL is equals to 2 times 10 to the power of 3 ohms. So now that we have XL, let's calculate VL. So VL is equals to 2 times 10 to the power of negative 3 times 2 times 10 to the power of 3. Therefore, it is equals to 4 volt. So the readings of V2 is equals to 4 volt. Questions 5 determines the readings of V3. So in this case, V3 is the potential across the capacitor. Therefore, V3 is actually equals to Vc, which is equals to IRMX XC. So to calculate Vc, let us determine Xc first. So Xc equals to 1 over 2 pi Fc. Substitute the values into the equations. Xc is then equals to 2 times 10 to the power of 3 ohm. Now, there's a shortcut for you to determine the values of Xc in this question. Why? Because at resonant frequency, Xc is just equals to XL. So we have XL from previous questions. Therefore, you can straight away apply Xc equals to 2 times 10 to the power of 3 ohm in these questions. So now let's calculate Vc. So Vc is also equals to 4 volt. Therefore, the readings of V3 is 4 volt. Question 6 determines the readings of V4. So V4 is the total potential across capacitor and inductor. Based on the phasor diagram for RCL circuit, the voltage across the inductor and the capacitor are 180 degrees apart, or you can say they are antiphase. Thus, V4 is the total of the VL and VC. And since they are facing towards opposite direction, so we have VL minus VC, which is then equals to 0 volt. Questions 7 determines the readings of V5. So V5 is the total potential across all three components. Therefore, it is equals to square root VR squared plus VL minus VC squared. Substitute the values into the equations and you will obtain V5 equals to 1 volt. So that's all for week 16. I will see you all again tomorrow.